Welcome everybody to example 3 of power series. So suppose we're given an expression like this and we're asked to find the power series expansion of this function. Well, we might want to know that we want to find the power series expansion around a particular point, or because there's kind of a variety of places that we could do this. And so let's just say that in this case that we want to find the power series expansion centered at x equal to 0. Okay. Well, kind of coming back to our geometric series, we know that our geometric series, when we had an expression that looked like this, of just x to the n, well, this was our power series. So this was kind of our first example of our power series, and we actually knew what kind of function that was really going to converge to. We knew that this was going to be our function 1 over 1 minus x. Now, where was that coming from? That was really coming from this expression. Oops, let's clean that up just a little bit more. Let's try that again. So that was coming from our expression x to the n plus 1 minus 1 over x minus 1 being our series expansion x to the n plus x to the n minus 1 plus x to the n minus 2 plus all the way down to x squared plus x plus 1. So we had this algebraic expression. We had this algebraic identity, and in the case that the absolute value of x was less than 1, we knew that this series was going to converge, so this actually went to our function 1 over 1 minus x as n goes off to infinity for the absolute value of x less than 1. And so we were able to actually come up with what would be our first example of a power series representation of a function. And so we can use this series to then figure out what the series for other functions might look like. Let's see how we can do that. So as an example of building up these power series, we take a series for which we know the expansion, and in this case it looks like n equals 0 up to infinity of just x to the n for our function 1 over 1 minus x. Well, if we wanted to do something like the power series expansion of 1 over 1 plus x, what is that going to look like? Well, I can make 1 plus x really 1 minus a negative x. And so now this becomes the expression that I then substitute into my power series. So here n equals 0 up to infinity. So instead of an x, I'm replacing it with a negative x. And so what do I end up with? I have a power series of the form n equals 0 up to infinity of minus 1 to the n times x to the n. And so this gives me a power series expansion for a 1 over 1 plus x. Kind of taking that one step further, if I have a power series expansion for 1 over 1 plus x, what I can do from there, so 0 up to infinity, this was a minus 1 to the n, x to the n. If I then have something like 1 over 1, how about a 2 plus x? What would I do in that case? Well, in this case, what we could do is I factor out a 1/2, or I factor out a 2 from the denominator. And so that's going to give me a 1 plus x over 2. So now I've got a 1/2 times my function 1 over 1 plus x over 2. So what happens in this case, I do the power series expansion again, but now I do a substitution with, so I have a minus 1 to the n. Instead of just x, I have an x over 2 to the n power. And so my power series expansion ends up looking like the sum n equals 0 up to infinity, whoops, my 1/2, of a minus 1 to the n over 2 to the n x to the n. And so if I want to bring that 2 to the inside, I can kind of get a final answer, n equals 0 up to infinity, of minus 1 to the n, 2 to the n plus 1, x to the n. And so this gives me a power series expansion for something of the form 1 over 2 plus x. So kind of as one final example, if we had something then that looks like x minus 2, how might we do this? Well, from here, again, I want to factor out a negative 1. So I factor out a negative 1, so that gives me an expression of the form 2 minus x. If I then do the same thing I did before and factor a 2 out of the denominator, I have 1 minus x over 2 on the inside. And so now I've got a minus 1/2 times 1 over 1 minus x over 2. So that in this case, I now can come back to one of my original power series, and so I have this minus 1/2 times my sum, n equals 0 up to infinity, of just x over 2 to the n power. And so what does this give me? Now I have a minus 1/2 sum, n equals 0 up to infinity, x to the n over 2 to the n. So now if I want to bring that 2 to the inside, I increase the power by 1. N equals 0 up to infinity of a minus 1 over 2 to the n plus 1, x to the n power. And so this gives me the power series expansion for 1 over x minus 2. Now, in all of these cases, we haven't really talked about the radius of convergence, but when we do the substitution, we actually do the substitution into the radius of convergence as well. And so for this case, I did a substitution of x over 2. Well, in my usual power series, I know that it's going to be something less than 1. So what substitution did I put in? I put in x over 2. And so in this case, what does my interval of convergence look like? I just have the absolute value of x is less than 2. And so I get a radius of convergence in this case of 2. All right, so coming back to the original problem that we had, we wanted to find the power series expansion of 1 over x minus 2 times 1 over x minus 1. Well, something that we can do is to turn to the partial fraction decomposition. So my partial fraction decomposition of 1 over x minus 2 times 1 over x minus 1 is going to be a 1 over x minus 2 minus a 1 over x minus 1. And so kind of breaking up into this form, now we can use the power series that we had before to figure out what the power series for this new function is going to look like. So our power series for 1 over x minus 2 was going to look like the sum n equals 0 up to infinity, a minus 1 over 2 to the n plus 1, x to the n power. And likewise for our 1 over x minus 1, this one was going to look like the sum n equals 0 up to infinity of minus 1, or just really a minus x to the n power. And so when we kind of put these things together in this form, we can do that as our sum n equal to 0 up to infinity of a minus 1 over 2 to the n plus 1, x to the n, minus our series n equal to 0 up to infinity of minus x to the n. And so if we kind of combine these two series together, which we're allowed to do, n equals 0 up to infinity, we've got a minus and a minus gives us a minus 1 over 2 to the n plus 1 raised times x to the n. Okay, so here we end up with a power series that has the form 1 minus 1 over 2 to the n plus 1. Let's clean that up so that looks a little bit better. Let's try that again. 1 over 2 to the n plus 1 times x to the n. So this gives us the power series expansion, but then what about the interval of convergence for this thing? Well, remember for our series 1 over x minus 2 that we had in our power series expansion, we had the minus 1 over 2 to the n plus 1, x to the n, and this one worked as long as the absolute value of x was less than 2. And likewise, for our series with just minus x to the n, that one was going to have a radius of convergence of 1 in that case. And so what happens for the series for our new function, well, it's going to be, since we added those together, these will be valid in the overlap of each one. So if I kind of look at the interval for the first one, the interval for the second one, I have 0 here. I can go out to 2. I can go out to -2. I can go out to -1. And I can go out to 1. Well, in the first series, I have everything in between -2 and 2. For the second one, I have everything in between -1 and 1. And so kind of where do those overlap? They're going to overlap right here. And so I can only take the x values that are kind of inclusive or work for both power series at the same time. And so in this case, I go with the more restrictive interval, and so my interval of convergence is actually going to be my integral, or my radius of convergence, n equals 0 up to infinity, that we had 1 minus 1 over 2 to the n plus 1 times x to the n. This was going to work for the absolute value of x less than 1. And so we've got our kind of radius of our power series and where this function is actually going to be equal to that value.